Hi, my name is Dane Quinn, and I'm from the University of Akron. And for today's video lecture, we'll do an example dealing with particle dynamics. We have a ball of mass m, given here at some initial height h above the ground. And if it's released from rest, I'd like to determine the time required for the ball to fall and contact the ground, and then its speed when the impact occurs, or in particular right before the impact occurs. So when I look at this problem, we find that the only force acting on the particle is due to gravity. Again, this is projectile motion. So we have a force due to gravity. So the only force that acts on the particle arises from gravity. Now we must define coordinates and directions that will allow us to describe the configuration of this particle. Here we've shown directions I and j in the horizontal and vertical directions. Then we would like to measure the height of the ball above the ground with a coordinate y. So note here that y measures the height of the ball at any given time. In particular, at time 0, the height is h, so that's the initial height. And with this coordinate, we find that the acceleration of the ball is y double dot in the j direction. So here, if I know y, and in particular if I know the second derivative of y, then I can describe the acceleration in this way. Now, in terms of these directions, the force acting on the particle can be described as minus mg in the j direction. So here we have the acceleration and we have the forces. Now we are ready to apply linear momentum balance. Which will lead to the equations of motion that describe the response of the system. Linear momentum balance is the sum of the forces acting on the particle is equal to the mass times acceleration of the ball. And we can go and fill in the left and the right sides. The only force acting on the particle was due to gravity, so that's minus mg in the j direction, while the acceleration was y double dot in the j direction. So, and the equation of motion can then be written as y double dot is minus g. So we have constant acceleration. In order to find the response, we'll integrate to find velocity. So here, y double dot, and we'll use tau as the dummy variable in the integration from 0 to t, again d tau, gives the following. Y dot at time t minus y dot at time 0. So again, this is the integral of the left-hand side because the second derivative of y is the derivative of y dot. So we have the integral of the derivative. And then the right-hand side reduces to g times t. Now, because the ball is released from rest, the initial speed in the vertical direction, so that's y dot, was equal to 0. Therefore, y dot, as a function of time, is simply minus g times t. And we integrate again to find position. So we'll take the expression for velocity that we just determined, which is y dot, and again tau will be our dummy variable for the integration, is minus g times tau. integrate over tau from 0 to t, and we find that y of t minus y of 0, again, that's the integral of the left-hand side, is minus g over 2 t squared. Here, the initial displacement of the ball, the height above the ground, is h. So using that information, we can solve for the position as y of t is minus g over 2 t squared plus h. So this describes the position, the height above the ground, and the speed in the j direction, both as a function of time. Let's go back and remind ourselves what we were looking for. We wanted to know the time required for the ball to hit the ground and the speed when the impact occurs. The ball impacts the ground at some unknown time. So we'll define that time as t equals t final. Again, t final here is an unknown time at which the ball impacts the ground, and the vertical displacement, which is y at that final time, is equal to 0, because the ball has fallen and struck the ground. So y is equal to 0 at the contact. As a result, we see that 0 is equal to t final, but the value of y also has to satisfy the response from the equations of motion. So that was minus g over 2, and it occurs at t final, so it's g over 2 t squared plus h. So if I look, this piece comes from the response of the system, from the equations of motion and the solution that we obtain by integrating the acceleration twice. While this piece comes from the final condition, namely the ball is at the ground at that final time. So the ball has to be on the ground, and the ball has to follow the response of the system as determined from the equations of motion. Now looking at the left and the right side, we can solve for t final. And we find that t final here is equal to square root of 2h over g. So this gives us the time at which the ball strikes the surface. And finally, when the ball hits the ground, the velocity of the ball is y dot in the j direction. So at this final time, y dot at t final is minus g times t final, again from the equations of motion. And now I can take this value of t final, put it right there. So y dot at this final time is minus square root of 2gh. And we've determined the final time and the velocity at this final instant. So here we've seen a nice example of projectile motion. Admittedly a fairly simple problem. We've taken a ball and we've released it from rest at some height, and we've asked for the time required to hit the ground and the velocity when it does so. Again, an admittedly simple problem, but it's nice that we've taken the dynamic response that we solved for from the equations of motion and combined that with problem-specific information, in particular the height at which the ball hits the ground is equal to 0, and we've used that to solve for the required information. So that's it. We'll do some more complicated examples later, but let's always start off with a simple example first. Thank you very much.